For a discrete random variable, the probability distribution is any table, graph, or formula that gives each possible value and the probability of that value. The total of all probabilities across the distribution must be 1, and each individual probability must be between 0 and 1. Nowadays, exist different types of variables for a discrete distribution. For example, Bernoulli, binomial, geometric, negative binomial, hypergeometric, and Poisson.
A Poisson distribution is a discrete probability distribution that tells from an average occurrence the probability of a certain number of events from happening during a certain amount of time. In other words, lambda equals entity over time. For example, lambda equals the amount of customers a store clerk will help in a minute. Graphically, the Poisson distribution looks like this. Whenever lambda equals 10, the graph will look like a normal distribution graph. And as the value of lambda gets smaller, the right tail will get larger.
A geometric distribution is a discrete probability distribution which will tell us the probability that an event will happen in the first and only try of the last event of a random experiment. In formula words, you can say that P is the probability of success on each try, and the small x is the number of tries necessary to succeed. You can also plot this and say that if you only need one try in order to succeed, then your x will be 0 because you succeeded at the time that you wanted to succeed.
A continuous random variable is such that all values to any number of decimal places within some interval are possible outcomes. A continuous random variable has an infinite number of possible. The total probability would be infinite, rather than 1 as it is supposed to be. The distribution has two functions, the density function and the cumulative function. Exist different types of variables for a continuous distribution. For example, uniform, gamma, exponential, normal, standard normal, and other ones.
Exponential distribution is the probability distribution that describes the time between events in a Poisson process. The exponential distribution is not the same as the class of exponential families of distributions. In the graph of probability density function, the line for each distribution meets the y-axis at lambda. Notice in the figure that when lambda is large, the time between events is small. In particular, the mean time between events is given by 1 divided by lambda. The probability that the time between events is less than a specified time x is given by the cumulative distribution function. The graph shows that using the cumulative distribution function with lambda 1, the value of x1 corresponds to a value of y.6.
A uniform distribution is a probability distribution in which all the outcomes are expected to occur equally. We can say that all outcomes are equally likely. In probability and statistics, the continuous uniform distribution is considered as a symmetric probability distribution, in which all intervals of the same length on the distribution's supports is equally probable. This is defined by two parameters, which are minimum and maximum values. In the density function, the two random variables have different supports, but their two supports have the same length. Therefore, since the uniform density is constant and inversely proportional to the length of the support, the two random variables have the same constant density over their respective supports. Because there are infinite number of possible constants, there are an infinite number of possible uniform distributions. In the cumulative function, as the graphic illustrates, f of x is equal to 0 when x is less than the lower endpoint of the support, and f of x is equal to 1 when x is greater than the upper endpoint of the support. The slope of the line between a and b is, of course, 1 divided by b minus a. One of the properties of the cumulative distribution function is that f is not decreasing and right continuous. In the case of a continuous distribution, it gives the area under the probability density function from -infinity to x. And the cumulative distribution functions are also used to specify the distribution of multivariate random variables. For two constants a and b such that a is greater than x and x is greater than b, a graph of the cumulative distribution function looks like this.